Hello! Now that you have a basic understanding of the lift force, let's have a look at the aerodynamic drag. Along the same lines as the lift equation, it is possible to write down an equation for drag. It depends on a pressure, the dynamic pressure, multiplied with the surface area, and finally multiplied with a non-dimensional coefficient, which represents the geometry and the angle of attack. For commercial aircraft, the maximum ratio between lift and drag, or the maximum ratio between lift and drag coefficient, is about 15. For specially designed airplanes such as gliders, lift-over-drag ratios in the order of 50 can be achieved. So a lift force 50 times as large as the drag force. It turns out that drag of a wing essentially can be separated into two physical factors. The profile drag, which is the result of the friction and pressure distributions mentioned before. This is fairly obvious. And the second is induced drag as a result of the formation of vortices. That, however, may be surprising to you. So, what happens? Whenever a wing generates lift, there will be a pressure difference between the upper and lower surface. At the wingtips, the air wants to flow from a relatively high pressure to a relatively low pressure. Due to this flow, tip vortices are generated. You should realize that these can be very strong. If a small aircraft would fly through the tip vortex of a large aircraft, it could result in a disaster. This has happened in the past, and as a consequence there are rules for separation between airplanes. So why does this result in drag? You can look at it in two ways. First of all, the air is moving when an airplane has passed. The wing deflects the airflow downwards. There is a so-called downwash and there are tip vortices. So the air behind the aircraft is moving and thus it contains kinetic energy. In other words, energy is left behind in the atmosphere. Effectively, this is drag. You could also look at it in a different way. Whenever a wing generates lift, it creates a downwash. This downwash effectively alters the free stream flow angle. It is slightly tilted downwards. As a consequence, the angle of attack, which is the angle between the body and the flow, is a bit lower than you would expect. The lift factor perpendicular to the flow is therefore tilted backwards slightly. The backward component is parallel to the motion of the aircraft and is therefore experienced as drag. Since drag has two physical sources, the drag coefficient of a wing can be split into two separate elements. First of all, there is the zero lift drag coefficient, and secondly, there is the lift-induced drag coefficient. It turns out that the lift-induced drag coefficient depends on the square of the lift coefficient, pi, and the aspect ratio A and the span efficiency factor. The factor A is the wing aspect ratio of the wing. It represents how slender the wing is. For wings with a high aspect ratio, the lift-induced drag becomes relatively less important. The span efficiency factor phi represents how the lift is distributed over the wing. In the ideal scenario, it is elliptical because this results in a constant downwash behind the wing. The lift distribution can be designed by the chord length and the twist angle of the wing. With a smaller chord, there is less lift force, and with a twist angle, the sectional angle of attack can be specified. A nice example of an aircraft with an elliptic lift distribution is the Spitfire. It has an elliptical wing to achieve this. A more practical approach, which is easier to build, is the use of a tapered wing. By using a tapered wing, a lift distribution that is almost elliptical can be achieved. From a manufacturing perspective, this is much simpler than an elliptical wing. Altogether, there is one equation, the lift-drag polar, that represents the relation between the lift coefficient and the drag coefficient. The lift coefficient is a function of the angle of attack as represented by the lift curve slope. Finally, there are two equations that relate the coefficients to actual forces. The information on this slide is all that is needed for aircraft performance analysis. with factors in the equations such as CD0, phi and the lift curve slope. It is important to realize that there are some parameters that will influence the values of the constant factors. The aircraft configuration plays a large role. With that I mean, is the landing gear deployed or the high lift devices? Second, there is the Mach number. This is the ratio of free stream velocity to the speed of sound. If this becomes larger than about 30%, compressibility effects start to play a role and factors such as CD0 will gradually change. This is especially important at high subsonic speeds in the region of Mach 0.8 up to Mach 1. The final remark I would like to make is with respect to the Reynolds number. This is defined as air density times the velocity times a characteristic length, such as the chord, and divided by the viscosity of air. The Reynolds number is an important factor with respect to the flow being either laminar or turbulent. It is essentially the ratio of inertial forces to viscous forces. The aerodynamics around very small objects can therefore be quite different than that of large objects.